Let's get started. Okay, so welcome everyone. It's my pleasure to introduce today's speaker, Klaus Fredenhagen from Hamburg. And he's going to talk about towards an algebraic construction of quantum field theory. And I just want to remind you that this talk is being recorded and will be put on our YouTube channel, so you can watch it later. So, okay, Klaus, the floor is yours. Please go ahead.
Okay, so thanks you for the invitation to give a talk in this seminar. Yeah, I want to report on certain progress in an algebraic construction of quantum field theory. And let me start with the, let me see. So, this is in the algebraic approach to quantum field theory, which most of you probably know very well, founded by Araki, Borchers, Hakasta, and others. And this is an approach which is based on physically plausible axioms, and it has shown to be well suited for the clarification of general structures, for instance, the interpretation in terms of particles, the spin statistics connection, the structure of superselection sectors, and in recent times, in particular, its relation to entanglement plays an important role. But traditionally, it has problems with the characterization of specific models. Of course, there has been some improvement in the last decades, for instance, in conformal field theory in 2 dimensions, on certain integrable models. But nevertheless, I think this is still a weak point of the algebraic approach. Now, what we try here is to add as a new ingredient algebraic relations known from formal perturbation theory. This is an approach which started in a collaboration with Detlev Buchholz and was then continued in a collaboration with Romeo Brunetti, Dütsch and Kasia Rejzner. Okay, what is the starting point? The starting point is renormalized perturbation theory in the causal approach. So the causal approach is something which goes back to papers of Stückelberg and is already proposed in the famous book of Bogolyubov-Shirkov, and was then mathematically clarified in all details by Epstein and Glaser. Now, the main point of this approach to renormalization is that one understands renormalization as a choice of time-ordered products of composite fields. And this choice is subject to a few axioms, and the most important of them is the causality axiom, therefore the name causal approach. Now, the causality axiom is very simple, and namely you require that you can define a time-ordered product of composite fields, and this product should coincide with the operator product if the point x is not in the past j minus of y of the other point y. And because of the structure of Lorentzian manifolds, globally hyperbolic Lorentzian manifolds, this fixes the product everywhere up to coinciding points. And this means that the time-ordered product is fixed by this axiom up to local counterterms. And as Epstein Glaser showed, this is exactly the freedom in doing the renormalization. So the freedom which is usually restricted by renormalization condition, but this freedom is just this freedom of the choice of local counterterms in the time-ordered product. Of course, to make it technically complete, there is a lot of work to be done, but this has been done in the past. Now, one can formulate this in the following convenient way. Namely, one looks in terms of this time-ordered product at the time-ordered exponential. which is then interpreted as the S matrix for an additional interaction. Now, the ansatz for going to use this in the algebraic approach to quantum field theory is that one considers these formal S matrices as unitaries in some C-star algebra. So for each local functional f of the fundamental field phi, we associate a unitary called S of f, which is realized in perturbation theory by this time-ordered exponential, but here it's just considered to be an element of an abstract C-star algebra. And then one looks at the algebra generated by these unitaries. This is a free C-star algebra modulo some relations, and one has to find the relations which give a structure to this C-star algebra. And the first of these relations is this causality relation, which then takes this form of that the S matrix of f plus g is equal to the S matrix of f times the S matrix of g, provided the supports of these functionals are causally separated, which means that the support of f does not intersect the paths of the support of g. Yes, this is just the translation of this condition, which I mentioned before, for the definition of the time-ordered product. Now, if one imposes this relation on this algebra generated by these unitaries, this gives already a Haar-Kastel net, which satisfies the axiom of Einstein causality. One associates a subalgebra A of O for some subregion O, and this algebra A of O is generated by the S matrix S of f, where the functional f has support in the region O. Of course, this does not say nothing about the dynamics. So how can the dynamics be formulated in this framework? And this can be done in the following way. Let L denote a classical Lagrangian. Let psi be just some compactly supported shift of the field configuration phi, and look at the difference in the Lagrangian. So we have the Lagrangian of phi plus psi minus the Lagrangian of phi. This gives some difference of Lagrangians, L of psi, or maybe better, the corresponding actions. And for a given functional capital F of the configuration phi, you define f index psi as f of phi plus psi. And then the relation which takes care of the dynamics is what we call the unitary Schwinger-Dyson equation, namely that S of f index psi, so the shifted capital F, plus this difference in the Lagrangian, delta L of psi, is equal to S of f. Now, when you differentiate these formula in perturbation theory, you just see what you get is the Schwinger-Dyson equation. So this is just the field equation derived from the Lagrangian L, and in perturbation theory, this leads to this word identity, the Schwinger-Dyson equation. And one can show that in perturbation theory, also this unitary form of the Schwinger-Dyson equation holds. But here we require this relation as a relation in this abstract C-star algebra. Now we can impose this relation, which defines a new quotient algebra. And this quotient algebra, with respect to the dynamical relation, is again a Haar-Kastel net, now characterized by a classical Lagrangian L. Now, this can be done for every Lagrangian, but it's interesting that you can pass now from one Lagrangian to another Lagrangian by the interaction picture. So it's well known that in algebraic quantum field theory, the interaction picture is, usually not present. One of the reasons is Haag's theorem, which tells that a certain form of the interaction picture cannot hold. But here we can see that we have a full interaction picture, but we need some preparation for this. Now, according to Buchholz, one can define the S matrices of the theory with an additional interaction V, provided V has a compact support and V is a local interaction. Then one can embed the theory with the new Lagrangian L plus V into the theory with the original Lagrangian L by this formula. You define S index V of F. This is the S matrix for the theory with interaction V. And this can be mapped to some element of the original algebra, S of V to the -1 times S of V plus F. This is a retarded version, or you can do it in the opposite way. This is the advanced version. And actually, what one can show is that this that this is really a map which satisfies the dynamical relation. Namely, the dynamical relation for the interacting theory would be that you have F index psi plus the difference of the Lagrangian, which is the difference of the original Lagrangian L and the difference of this new interaction V. And when you insert the definition, you get in two steps that you get the S matrix of the original function F. So this unitary Schwinger Dyson equation for the interacting theory is automatically satisfied. But we would also like to have the causality relation. And the causality relation is not necessarily satisfied. Namely, let us assume again that F and G have causally separated support. Then we define the retarded interacting theory for F plus G. And we look at the product of the two S matrix, SV red of F, SV of G. And then you see, in order to have this causality relation for the interacting theory, you need an improved causality relation, namely this relation that S of F plus V plus G is equal to S of F plus V times S of V to the -1 times S of V plus G, provided the supports are causally separated. And this relation should hold for any V. Yes, this is should be completely independent of V. Now, what can one say about this relation? Actually, this relation you find already in, I think it's already in Buchholz's work, and it's more analyzed in the famous paper of Epstein and Glaser. And actually, it turns out that this relation already follows from the original causality relation in perturbation theory, and in more general terms, and provided S of F is a power series in the functional F. But in our abstract framework, it is a stronger condition. Of course, one has to add the condition that S of 0 is equal to the identity. And there's a further complication which does not occur in perturbation theory, namely if this interaction V contains also kinetic contributions, so contributions which involve the kinetic part of the Lagrangian. So the metric occurring in the Lagrangian is changed, and then also the causal structure can be changed. And this means that in this improved causality relation, one should not use the original causal structure, but the new causal structure, which is induced by the interaction B. So this is a non-perturbative aspect which has to be taken into account. But if this is taken into account, then one can do the following, then looks at this improved causality condition and the dynamical relation, and gets for each pair of a space-time M and a Lagrangian, which classical Lagrangian, which imposes which has a kinetic term which makes M to a globally hyperbolic space-time, a H-castellanate. And these different algebras with different Lagrangians are actually, by this Bogoliubov map, isomorphic to each other.
Excuse me, may I ask a question?
Yeah.
So you assume from the beginning that M is a globally hyperbolic Lorentzian manifold. Is it correct? So
yes. So the Lagrangian is so that it for the Lagrangian always has this kinetic, usually kinetic part, and there's a metric. And for this metric, the manifold is globally hyperbolic. Yeah.
Yeah. So the space-time does not have to be a Minkowski space, but a more general.
It can be more general. Yes.
Okay. And what kind of Lagrangians are allowed in this theory?
So Lagrangians. So here we did this for scalar fields. So the Lagrangian has a kinetic term, standard kinetic term.
Yes.
Plus some polynomial in the field, perhaps with one first derivative, but not with other second derivatives or products of first derivatives.
So the interaction can be linear in the first derivative, but not
more. Yeah.
Not more. And you can have several fields.
Several components. Yes.
Yes. Okay. Okay. So the kinetic term is quadratic in the derivatives, and it has to be compatible with the causal structure of space-time. Is it correct?
Yes.
Okay.
Yeah, this is the assumption.
Yes. Thank you.
Okay. So by this construction, one can show that the global algebras for different interactions are isomorphic to each other. But this does not mean that the theories are the same, because according to the principles of algebraic quantum field theory, the structure is in the association of subregions to subalgebras. So the position of the local subalgebra is changed by the interaction, but not the global algebra. The global algebra is always the same. Now one can try to make this more explicit by looking at a special Lagrangian. Here we take the free Lagrangian. So this is just a metric, inverse metric applied to the differential of the field, and a mass term. And we look on not at the most general functionals, but at linear functionals. So just a field integrated with some test density. And in addition, we assume that the S matrix of a constant is just e to the I times this constant. This is can always be done. This is a central element, but it's convenient to choose it in this way. And then one can compute the product of two such S matrices in this abstract algebra. And it turns out that you get this product relation, which is nothing else as a Weyl relation. So this is just the version, the unitary form of the canonical commutation relation, which here comes out just from the causality axiom. The causality axiom together with this dynamical axiom implies the canonical commutation relation in the Weyl form. And this, I think, is quite surprising that you don't have to impose the condition of canonical quantization. This was done by Detlev Buchholz and myself. Now, the Weil algebra, so this algebra generated by these linear functionals, is known to be a simple algebra. And in particular, it also satisfies the time-slice axiom. The time-slice axiom says that the algebra for the full space-time is equal to the algebra of a subregion which contains some Cauchy surface of the space-time. Yeah, this is the situation, and this describes in an abstract way that there is a specific dynamics, so that the future and past can be computed from the present. This is no longer true for the full algebra. The full algebra can be shown to admit a large class of automorphisms which act trivially on the Weil algebra and map local algebras into themselves. And these automorphisms are of the form that you apply some map Z to the local functional capital F, and this map Z maps local functionals to local functionals. It acts trivially on linear and constant functionals. So in particular for the Weil, if F is a linear functional, this Z is the identity. It preserves the support, so the local structure is not changed. And it should also respect the other structures, so the additivity relation, which Z has to satisfy, guarantees that the improved causality condition is satisfied. So if the supports of these functionals are disjoint, of the function f and h are disjoint, then you have this additivity relation here. And the unitary Schwinger-Dyson equation is preserved if you require this condition for z, so z of this shifted f plus the delta L of psi gives just the z of f's shifted and then you add the difference in the Lagrangian. And then you look at the group of invertible transformation Z, and this group can be interpreted as a non-perturbative analog of the renormalization group in the sense of Stückelberg-Petermann. So in the renormalization group, as defined in the work of Stückelberg-Petermann, characterizes the ambiguities in the renormalization process. And this ambiguity can be described in terms of a map which maps local functionals to local functionals. And here we have just the same, in principle, the same situation. So we have a group of invertible transformations which map local functionals to local functionals, satisfy a few conditions. And this group changes the nonlinear, the S matrices of nonlinear functionals in a non-trivial way. And in particular, and so they can have compact support, so you can make a change. This automorphism can change non-trivial in the future, and so this the time-slice axiom cannot hold. So this is a concept of the renormalization group according to Stückelberg-Petermann. This is not the same as the Wilsonian concept of the renormalization group. It's related, but it's not not identical. Yeah, so actually this was discussed in a joint paper with Romeo Brunetti and Michael Dütsch, how these two concepts of the renormalization group are related to each other. Okay, now one can look also at the version of this renormalization group if we go from a free Lagrangian to an interacting Lagrangian. And then we indicate this by an upper index V. V is the interaction, and define the Z upper index V as Z of V plus F minus V. This implies in particular that now this renormalization group element applied to 0 is no longer necessarily 0 in general. And so when we define an isomorphism for the interacting theory, we should use either the retarded or the advanced version. So here this is a retarded version. So we have this S matrix with ZV of F, and we have to multiply it by the inverse of the S matrix of ZV of 0. Now, how can we understand this automorphism, this isomorphism? We can understand it in terms of this retarded embedding, because we can embed the interacting theory into the free theory. We insert the definition, and what we get is the following. We get the S matrix for the transformed interaction Z of V, and we apply it now not to the original functional, but to a functional Z lower index V of F, where Z lower index F of V of F is defined as this difference, Z of V plus F minus Z of V. So we see that the renormalization group element changes the interaction. V goes to Z of V, and also the functional which characterizes the observable. Okay, now this is a certain freedom in this, or this ambiguity in this construction up to now. Now we look at symmetries of the configuration space. And we can look at different symmetries. So for instance, here we consider linear field redefinitions, which means that we apply a matrix to the field. So the field is an n-component field, and we apply a certain matrix to this field. And the matrix might depend on the point X. And here we look at smooth matrix-valued functions with compact support. And then this gives also a transformation of the functionals. So A applied to F of the function F is just F of A transposed applied to phi. And of course, in the same way, we can do a transformation of the Lagrangian. And what we see is that then we get some automorphism of our isomorphism of our algebra. Then we map S of F to S of A star F. And this is an isomorphism of our algebra associated to M and L, to the algebra with a new Lagrangian A star. Yeah? So this is just, in a sense, a redefinition of your fields. But the non-trivial point comes now, namely, we can also compare the changed Lagrangian and the original Lagrangian, and they differ by some compact region. And we can take the integral, call this delta A of L, and consider this to be an interaction. And so we can embed this algebra with the changed Lagrangian into the algebra with the unchanged Lagrangian L. And this by this retarded embedding, and get a map. S of F goes to the retarded version of delta AL applied to A star F. And so what we get, this map S of f goes to S of delta AL up to the -1 times S of delta AL plus A star f. And this is an automorphism of the original algebra. Yeah, so we first change the functional, and then we consider this difference in the Lagrangian as an interaction. Then we can try to compute this automorphism. And for the free Lagrangian, we can compute this on S matrix S of f for linear function as f. And there we find that actually this automorphism is trivial. Now, if the functional is not linear, then one cannot expect that this is always trivial. But what one can conjecture is that this is exactly a renormalization group transformation as discussed before. So we postulate the following relation. We assume that there exists a map zeta from the group generated by field redefinitions A to renormalization group elements zeta index A is such that for all local functionals, S of delta AL plus A star f is S of zeta A of f. Yeah, so in the dynamical, in the unitary Schwinger Dyson equation, we had to change by a shift. And there we always required that on the right-hand side, you get the original function f. Here, we admit that there is a certain change in this functional f, changed by some element of the renormalization group. And this identity we call the unitary anomalous master word identity. The map zeta has to satisfy a certain co-cycle condition, which is written here. So if A and B are these matrix valued functions, then zeta of the product AB is zeta B times the transformed zeta A transformed by B, and the action of B is defined in the following way. So if Z is a renormalization group element, then Z index B is just this conjugated action of transformation B index L. And what is B index L? This is just the action of B on the function f plus the induced change of the Lagrangian.
So, excuse me. So one can view this as an additional axiom, the existence of zeta, or is it a consequence of the?
No, it's an axiom.
Okay.
It's an additional axiom.
Okay, thank you.
Yeah. No, it's not satisfied for the original algebra.
So
this is just an additional relation, independent.
An additional relation that narrows down the algebra.
Yeah, that's true. Yeah.
Thank you.
Okay, now we did this here for these linear field redefinitions, but you can do it in the same way also for compactly supported diffeomorphisms of the manifold M. So this diffeomorphism changed the configuration just by composition. And then they changed the functionals just by this definition. And they changed the Lagrangian. And you can look at the change of the Lagrangian delta chi L, and requires the same relation for diffeomorphisms. And then, of course, you can generalize this to look at the group generated by all these transformations, so the shifts psi, the linear field redefinitions A, and the diffeomorphisms chi. And then this general unitary anomalous master word identity postulates this equation here for some co-cycle zeta. Now this relation, if zeta is given, yeah, zeta is just the only condition which zeta has to fulfill is that it's a co-cycle and that it has it maps into the renormalization group. And then zeta defines a certain ideal in this original algebra. We can look at the quotient, and this quotient has local subalgebras. And this is now a Hakastel net defined by the Lagrangian L and the cocycle zeta.
Excuse me, what are capital Fs? So these are functionals.
These are functionals, yeah.
Yeah, what class of functionals? I mean, not only linear.
Not only linear. Actually, there is some freedom. So you could use all polynomial functionals, for instance. Or you can also restrict the degree of the polynomials. I think here this for the formalism up to now, this is you can just take any class of functionals which is closed under these operations which are used.
What about their locality? Can they be?
They should be local. They must be local functionals. Yeah, so just integrals over, you have a function on the jet space, and yeah, and so it should be local functionals. But there you have a large freedom of. You can here up to now these functions can be arbitrary local functionals. This compact support.
Okay.
Always compactly supported. Okay, and then of course then this can be always be done. So this is in the sense abstract nonsense. You can really just formulate these conditions. The question is then, is this consistent with what we know from perturbation theory? And the answer is yes. Can be shown that this unitary anomalous mass-about identity holds in formal perturbation theory. And there is also where the name comes from, namely there's the anomalous mass-about identity postulated by Brennecke and Dütsch, which is actually equivalent to this unitary form, the identity. And it appears in a somewhat different form in the renormalized quantum master equation of the Bartalin-Wilkowski formalism, as done in a paper with Kasia some years ago.
Sorry, can I ask a question?
Of course.
Concerning the theorem, I mean, this perturbation theory refers to a specific model, or I mean, how should I understand it? I mean, are we doing perturbation theory for a specific model, for a class of models?
Yeah. So perturbation theory. No. Here you have you start from in perturbation theory. You start from the free theory. Mm-hmm. And then but in this Epstein-Glaser formalism, you allow any local functional as an interaction. So say any polynomial functional usually, but in principle, you could also have non-polynomial functionals which admit power series expansions.
And dimensionality does not play a role here?
The dimensionality does not play a role here, yeah.
Okay.
And what is delta sub G?
Oh, this is just the difference of the original Lagrangian and the changed Lagrangian. And then, so in a sense, this is the just the change of the Lagrangian.
Okay. But then just so
you have this symmetry. You look at the symmetry and you compare the two Lagrangians, the usual Lagrangian and the old Lagrangian. Compute the difference.
So, but this identity entered as an axiom in the general formulation, and then what I understand is that now this is true at the level of formal perturbation theory for a certain class of polynomial perturbation of the free field. Is it so?
Yeah. So you, of course, in perturbation theory, you have some restrictions what you can do. Yes, so you can start from a free theory and you can treat polynomial interactions.
And then this means that if one chooses a specific theory, then the zeta G is also fixed, I guess. I mean,
so you don't have to choose the interaction. The interaction is completely free here. You start from the free theory, but then in perturbation theory, but then you can do any interaction.
But I'm saying that the zeta G is determined by the interaction. I mean, this is a model-dependent quantity, this zeta G that I see on the right-hand side of the
so you can first look at L as a free Lagrangian, yeah? But by this, by the validity of the interaction picture, which I mentioned, this can automatically translate it to any other interaction. Yes, so it's sufficient to have it for the free case, but because the interaction picture is here completely satisfied, you can do it for any interaction.
Okay, thanks.
Yeah.
Excuse me, I forgot what is capital script G. I mean, the lowercase g belongs to the capital script.
Yeah. It's a capital, the script G is a group generated by all these transformations which I discussed. Shifts, linear field redefinitions, and diffeomorphisms.
The diffeomorphism of the underlying space-time?
Of the underlying space-time, but compactly supported. Yeah, everything compactly supported.
So shifts psi. So you what is a shift?
Shift means just you have a field configuration which is a function with just a smooth function, and you add a smooth function with compact support.
Okay.
Yeah. Okay, so this is this abstract formalism, and now one can analyze the arising Hakastel net. And actually, this was a great surprise for us. Namely, what one could prove is that this new Hakastel net, which was obtained by adding this co-cycle zeta and looking at the quotient algebras, that this new net satisfies the time slice axiom for any choice of zeta. Another consequence is that you find a certain form of the Noether theorem, which we call the anomalous Noether theorem. Namely, when you have a symmetry of the Lagrangian, then you can always find unitary implementer of this symmetry, which actually give almost the transformation up to some renormalization group transformation. So the classical symmetry is somewhat modified by a renormalization group transformation. So this is called, maybe understood as a quantum symmetry. And then there are, of course, cases where you have the zeta vanishes, so it means that it's trivial. Then the classical symmetries really coincide with the quantum symmetry, and you get the ordinary Noether theorem in this unitary form. So you get these conserved currents, which you know from the Noether theorem, now in the exponentiated form. So you get something like local charge operators, which really implement the corresponding symmetries.
Klaus, there's a question on the chat, but I think it was already answered. So it was about the existence of a C-star norm, but yeah, that I think is already clarified.
Is it clarified, or?
No, the question was, how do you know that the algebra with these relations actually admits a C-star norm?
Yeah, no, I did not mention this. So this is a general construction, because here these relations define a group, and every group has a unique C-star, a group C-star algebra. So you can look at the group algebra, and the group algebra has a maximal C-star norm, and this is the associated C-star algebra.
Yeah, I think, yeah, that should, okay, yeah, that answers it, yes.
Okay. Yes, so then the last point here in this list is that when you have symmetries of the Lagrangian, then they induce the flow of theories which can be described in two equivalent ways. One is obvious from this formulation, namely, when you look at this H-Kastler net and you have a symmetry of the Lagrangian, it just acts non-trivial on zeta. So the flow is described by a change of this cocycle zeta. But what one can then prove using these renormalization group transformations is that it's equivalent to another description of this flow, namely where the Lagrangian is changed. And in addition, also the observables are transformed. This is a more standard or traditional way of describing the flow of the renormalization group. So here we have two alternative ways to describe the same thing. Okay, now the proof of these properties is somewhat involved, and I want to say a few things about the proof that the time-slice axiom holds. Actually, how much time do I have?
Yeah, we started a bit late, so like, well, 14 minutes, I would say.
Okay, fine.
That order of magnitude.
Okay, so yeah, so this is of course only a sketch. The full argument is somewhat involved. So we start not from a general Lagrangian, but from a special Lagrangian, which is stationary. So it has a time translation symmetry and is of second order. So it's a free Lagrangian. Then we look at some functional f and then choose some a such that the support f is contained in the region where the time variable t is smaller than a. And we assume that a is positive. So we are somewhat in the future. We want to show that we can restrict everything to a small neighborhood of the time zero hypersurface. So we choose now a diffeomorphism which does not increase the time, so it goes a little bit into the past. And in a certain neighborhood of the path of the support of our functional and above the times larger than a over 2. This should act as a time translation by some quantity minus tau, and tau is somewhere between 0 and a over 2. Then we use the fact that L is stationary. So it means that L is invariant under time translations. So this means that the delta chi of L has no intersection with a certain region. It's just this region, the image under chi of the region where the diffeomorphism acts as a time translation. And so there's a certain region where which is not in the support of delta chi L. And then we split our change of the Lagrangian delta chi L into two parts. One, which does not intersect the path or the image of the path of the support of F, and another part which has support at times smaller than a over 2. So I think one needs a little bit time to really control all these restrictions. But I think the basic idea is because there's this region, intermediate region, where the differences of the Lagrangian is 0. This allows to separate this delta chi of L into these two parts, and one more in the path and the other so that it does not intersect the paths of our observable. And furthermore, we have a free Lagrangian, so a quadratic Lagrangian. So for a quadratic Lagrangian, first of all, by this unitary anomalous mass-about identity, S of delta chi L is just S of the zeta chi of 0. But for the free theory, the renormalization group transformation at 0 gives 0. Or at least it's always a constant. Cannot be non-trivial. It cannot have a non-trivial dependence on the configuration. And this is by assumption element a multiple of the identity, complex multiple of the identity. And moreover, for the free theory, these renormalization group transformations preserves the support. So this, when the support of F is in the region O, then also the support of this transformed F is in the same region O. So this allows us to apply the law of the causal factorization. So we have S of F by the mass-about identity. We can write it in this form, delta chi L plus chi star applied to the inverse, zeta chi to the -1 of F. Now we insert for delta chi L this decomposition in H plus H minus, use the fact that H minus and chi star of zeta chi to the -1 of F are causally separated. So we can use this formula for causal factorization, this improved causal factorization, get these three terms, product of these three terms. Now the first term is just a multiple of the identity, so this can be ignored. But then the other terms have functionals which have support in the region T smaller than A minus tau. Yeah, the support of F is moved by chi, and the support of H minus var by definition in the region T smaller than A over 2, and tau is smaller than A over 2. So we see that by this operation, we compress the support of our functional. Yes, we have the functional F here, and we have on the right-hand side other functionals, and they have a support in a somewhat smaller region. Then we iterate this argument and get something which comes from above, nearer to the time zero plane. And we can do the same with the opposite time in the opposite time direction. And at the end, we get something which is contained in an arbitrarily small neighborhood of the time zero plane. So this is the argument for the time slice axiom for the special case of a stationary free Lagrangian. But because we have so good control on the interacting theory, we can then use the interaction picture to draw the same conclusion for an arbitrary interacting, not necessarily stationary Lagrangian. Yeah, so this is a short version of a proof which in our paper takes quite several pages. So it's but maybe you got the crucial elements. The crucial element of the argument is that there's a certain region in where the Lagrangian is invariant, and we then use this causal factorization together with the interaction picture. Now the other results here are obtained in a similar way. So it's always the idea you use this symmetry, use the fact that the Lagrangian is not changed in a certain region. Then you can split this change of the Lagrangian into two parts. And these two parts then correspond to these unitaries implementing the symmetry. And okay, so this is essentially the argument. Yeah, I want to come to an end. So we have demonstrated that the algebraic construction yields a definite algebraic quantum field theory, which satisfies the axiom of locality, covariance, and time slice. So covariance I did not discuss, but this is automatic in this approach. It is fixed by two ingredients, a classical Lagrangian L and a co-cycle zeta characterizing the anomalies. So we restricted ourselves here to scalar fields. Fermionic fields can be treated similarly. There is some complication. You have to add auxiliary Grassmann parameters in a consistent way. This was done in a paper with the same authors. Actually, it's not completely trivial to do this in a consistent way. So it was surprisingly complicated, but I think we found a satisfactory solution. Then this structure is non-trivial in a certain way because we can use perturbation theory to get a non-trivial representation of a dense subalgebra in terms of formal power series of Hilbert space operators. And in particular, the scaling anomaly for massless scalar theories and the axial anomaly for massless Fermi fields can be recovered. There are a lot, of course, also many open problems. So one I already mentioned, this is gauge series. These gauge series are not yet included. I think there's one work in progress, so we don't expect, too many problems, but I think at the moment it's not ready. An important point is that this is a C-star algebra, and the C-star algebra has a nice property that it has a full state space. And always a faithful Hilbert space representation. So we know from the beginning that we have sufficiently many states. This, of course, does not replace a physical interpretation of the state space. This we don't have in this abstract framework. Yeah, so it would be nice to know more about the state space. We would know how it can be physically interpreted. And this is work which still has to be done and which might be very complicated. Another important point is the choice of this cocycle zeta. In our construction, zeta is completely free. But when we look at perturbation theory, there is Stora's main theorem of renormalization. And according to this theorem, the equivalence class of this cocycle zeta should be fixed by the standard stability requirements. So, for instance, when we have an existence of a vacuum state or of KMS states, particle interpretation or similar things. And so I think as a proposal for future work, which actually at the moment I have no idea how to do it, but I think this would be a very interesting project. find the equivalence class of the cocycle which characterizes the spectrum condition. Actually, the way the spectrum condition enters the algebraic framework of algebraic quantum field theory is an old problem which has no satisfactory solution up to now. So perhaps if we could be able to find the distinguished equivalence class which corresponds to the spectrum conditions, this could be possibly a satisfactory answer. But this is at least at the moment completely open. So I thank you for your attention.
Thank you very much, Klaus. So let's thank our speaker for a very nice talk. Yeah, there were already many questions, but I hope there are more. So the floor is now open for questions. Please unmute yourself and just go ahead.
May I ask a question?
Absolutely.
So suppose the manifold is just the Minkowski space with all its symmetries. Now, so in this framework, one usually assumes that there is a representation of the Poincaré group, that there are generators of space-time translations which satisfy the spectral condition.
Yeah.
Now, can you? I mean, I'm sort of afraid that. I mean, this is a C-star algebra, as you said, like an algebra of a discrete group. So yeah. I'm afraid that a translation, a space translation, is not a continuous. I mean, that it is difficult to implement it.
Yeah, I think you're completely right. So in the translations don't act continuous on this C-star algebra.
Yes, yes. So
as we know it from the Weil algebra. Yeah,
yeah,
so,
absolutely. Yeah.
Yeah. So this is certainly a problem that you actually, this is an old problem in this C-star algebraic formulation, that you usually cannot expect that these standard symmetries act continuously on the C-star algebra.
Yeah, but
this is also here.
Yeah, you certainly want a representation which where these symmetries are continuous.
No, the representation, they would be strongly continuous.
Yeah, strongly continuous.
But this is not a property of the C-star algebra, it's a property of the representation.
Yeah, so I mean, you will, can you expect that, I mean, you essentially didn't say a word about states, about...
So I said there are many states.
Yeah, yes,
but
yes.
We don't know whether there is a state that, for instance, translations are strongly continuously implemented. Yeah. So there are. One can even find invariant states, but these invariant states, in these invariant states, the translations don't act continuously.
Mm-hmm.
So one, it's not clear whether they exist.
Yeah, yes.
And actually, in general, one would not expect that they exist because this algebra is, in a sense, too large, because we admitted all local functionals. Think of, say, 5 to the 4, yeah, you would not expect that higher polynomials that the fourth power are well defined.
Yeah, so
you would restrict this to a certain subalgebra.
Yeah,
actually, what we know is that we can do it for the quadratic functionals.
So the physical algebra will probably have to be restricted even more.
Yeah, one would so typically what one does in causal perturbation theory, if one is interested in special interaction, one looks only at this interaction and all subpolynomials. Yeah, because they arise automatically. But not, you don't need the higher order polynomials.
Mm-hmm. This construction was valid for any dimension of space-time. Yeah. So
you cannot expect this large algebra has these nice representations in all dimensions. Mm-hmm. This you cannot expect. Yeah, so this algebra exists. This is a well-defined algebra, but it has, of course, also well-defined subalgebras. And when you look at representations, might be that these representations have nice properties only on these subalgebras. But this is largely open. I think at the moment we cannot offer results in this direction. We have always this subalgebra of linear functions, so the Weil algebra. There, of course, we know a lot. We can say something about quadratic functionals. And then in low dimensions, one can say a little bit more about other functionals. For instance, Sine-Gordon is a nice place, nice situation. Sine-Gordon in 2 dimensions. There one can construct the algebra and construct a representation where everything is very nicely represented.
What about the Hadamard condition for a state? Can it be formulated in this framework?
I don't think so. This Hadamard condition is related to the spectrum condition, and I think this is still no, it's not clear. So for instance, but from this analysis of the anomalies, we know that anomalies are unavoidable if you impose the spectrum condition or you impose the Hadamard condition and things like this. But in our abstract framework, we could choose zeta to be the identity everywhere. This would be a well-defined sister algebra. But it's not the sister algebra we are looking at. We would like to have a sister algebra where the spectrum condition is satisfied. But what is missing at the moment is a characterization of the co-cycles which admit the spectrum condition or admit the Hadamard condition. This is I think, the crucial open problem.
Thank you.
Thank you. Any more questions?
Jakob is.
Oh, Jakob.
Yeah. Hi. Hello, Kasia. Hello, Klaus. Hello, Klaus. Well, it's a minor question, but it concerns your. Did I understand correctly that if you have a quadratic Lagrangian, then you have a canonical commutation relations automatically?
Yeah.
So that somehow reminded me of the Jost-Schroer theorem in Weidmann field theory. But there, of course.
Yeah. Oh, yeah. This is an interesting connection. I did not think about it. Yeah.
There, of course, you have, however, you use the standard proof. You use spectrum condition, but which you don't have here.
Yeah. I think it's a mechanism in this Jost-Schroer theorem is different, but there might be a connection, yeah. But actually here, this what enters is only that you have a globally hyperbolic space-time.
Yes.
And so, for instance, it would also work for tachyonic theories. As the Jost-Schroer theorem makes no sense.
Yes.
So it's also on curved spacetime, it can be formulated, but also the Jost-Schroer theorem cannot be used.
Yeah.
So I think the mechanism is different, but it's interesting.
Similar in spirit, at least.
Yeah.
Okay. Thanks.
Thanks, Jakob. Okay, so there's another question on the chat. So under what condition would you refer to a theory in this framework as renormalizable? When there exists a co-cycle consistent with the spectrum condition? Question mark.
Yeah, I think this is a possible option, yes, but since we don't know almost nothing about this, in the moment this is a wild speculation. It's just a possible direction. It's not, yeah, I think at the moment it's difficult to say more.
Any more questions? Okay, well, maybe one more question from me, which I can also ask to myself, but since you're here. Yeah, so what other relations would one want to implement in that algebra? I mean, obviously, it's a very large algebra at the moment, right? So what are other physical relations that maybe one should think about? I mean, there's the spectrum condition, obviously, but what else is there that one should look at?
Yeah, I think for me it's essentially only the spectrum condition.
Spectrum condition, okay.
I think the other symmetries are there, and I think we have seen how renormalization acts. So it's just that at the moment the missing point is that we have no a priori information on a good choice of this co-cycle zeta. And from physics we would expect that the spectrum condition gives the restriction, but this is just yeah, what one may guess from perturbation theory. It's not an intrinsic argument.
Right. Yeah. No, so something like this should be there.
Yeah, maybe one. May I ask one question
Sure.
more in connection with what you were asking, namely, well, in the very, very old paper by Sergio Doppler about the algebraic spectrum condition, there is, of course, always the assumption that you have the translations as an automorphism. Yeah. That you can have the spectrum ideal as a left ideal, and you can ask that your representation as annihilate this ideal.
Yeah.
Likewise, in the Borges algebra, of course, there you have a definite spectrum ideal. But so the problem here is that you don't have any continuously acting translations a priori.
Yeah. I think this is a problem with Doppler's spectrum condition.
Yes.
It makes sense only if you have if your translation group acts continuously
on the algebra. Yeah.
And this is missing here. So this. I think there is, I have to have a look into the book of Borges on the translation group.
Yes.
Where he analyzes the subset of the state space where the spectrum condition makes sense. Yeah, so in a sense, this is the analysis which one has to do here.
Yes.
But unfortunately, this is very abstract, and it's difficult to to really get some information on this. But I think this is the direction in which I think further research is necessary.
Okay.
A small remark.
Hi, Eli.
It may be a silly one, but it's just the fact that you've got on the screen here that the C-star algebra has a faithful Hilbert space representation. This is in a way a little bit misleading, because we are not interested in faithful representations of this thing, because we want to be very unfaithful and quotient out a lot of junk that is in there, I think.
you mean that?
So
Yeah, in a given model, you expect to lose information, right? Or like, is that what you're trying to say? Or
so we're going to need to quotient more than we already have in this construction. So the physical representations are not going to be faithful representations of the C-star algebra.
Oh, no, they are usually faithful representations. No.
Really?
No. For the Weil algebra, we have faithful representations. This is the free field Fock space representation of the Weil algebra is faithful. So in a sense, one would like to enlarge the C-star algebra locally to von Neumann algebras, which would mean that you have a certain subset of the state space which are the potential locally normal states. But I think all this is related to the spectrum condition. Yeah, so and I'm also a little bit skeptical to say that certain states are unphysical, because state is just describes the possible values of observables. So the singular, so-called singular states are just extreme cases.
Okay, but
may I have another question? So
yes.
The starting point of the construction is Lorentzian manifold M.
Yeah.
Lagrangian, you described what class of Lagrangians, so we are interested. This mysterious zeta, but I thought that there are also some other, that there is also more input. You mentioned the class of functionals. Does it matter? As I understand, the construction depends on the class of functionals that you take, whether you take all polynomials or only quadratic polynomials or things.
Yeah, so you can look at all these functionals, or you can look at certain sets of functionals, and these correspond to subalgebras of this larger algebra.
Okay, so there are more data than what is listed here. Is it?
I would not say these are more data, but in a sense you can restrict yourself to some subalgebra. So when you construct states, yeah, then sometimes it might be possible only to fix a state on a certain subalgebra. Then you can decide whether this is enough information. You can, of course, extend always the state on a subalgebra to the large algebra, but this is not unique and perhaps difficult to specify this extension. Yeah, so in a sense, you would like to have states which have nice properties on some subalgebra, some good subalgebra. And this is, of course, not fixed. This is a matter of choice and depends on the problem you want to solve.
Mm-hmm. May I make one remark on this discussion about the simplicity of the algebra? Klaus, you mentioned that the Weil algebra is simple, but that's one of the points stressed by Detlev Buchholz in presenting his resolvent algebra, his and Hendrik Grundling's resolvent algebra, is that algebra has lots of ideals.
Mm-hmm.
And so, and you need that that's for non-relativistic situations, and for different dynamics, you will have different ideals. If you perturb dynamics by some compact operator, then you have then you have a different, so to say, dynamical ideal, and so that is, if I understand him correctly, he regards this as a very important feature of his algebra, that it's not simple, it has lots of ideals, so it allows lots of different dynamics, the same algebra.
Mm-hmm. Yeah, so I think this is true, and actually I don't claim that the algebra we constructed is simple. So the Weil algebra is simple, but this larger algebra I don't know.
Might not be.
No,
This I don't know. Probably it's not simple. This I don't know. But actually, I thought also about this question whether one could make a similar construction as this resolvent algebra also in this framework. But here it's not so clear whether one can do this, because these S matrices have a direct interpretation as operations on the system.
Yes.
And so it's not so clear that one can reasonably replace it by something like resolvents. Also, these time-ordered exponentials, yeah, I think they are not one-parameter groups. So you cannot easily, if you assume that they have some, can be integrated, cannot go to the resolvents in the same way.
Yes.
So this is not so clear. So my impression is that these resolvent algebra are especially nice in the non-relativistic situation because you don't have good locality properties in the non-relativistic situation. And here in the relativistic situations, you have these good locality properties. So in a sense, you don't have to worry so much about these things which go to infinity arbitrarily fast.
Yes.
And so it's,
yeah, that's a good point. Yeah.
Yeah, but certainly it would be nice if one could get to so we have this more or less discrete topology on this group of S matrices, and if one would have another topology there would be nice, but I don't know how to do it.
Okay.
So
yeah.
So now you're saying that there are ideals.
There might be ideals.
No, there might be. I don't know.
Okay.
Yeah.
But might there be ideals that you want to push and doubt?
Yeah, no, it could be, but okay.
Because if there's an ideal that you want to push and doubt, then you should only consider states that kill that ideal.
Yeah, of course.
And thus, you're not interested in. You would not be interested in faithful representations.
But wait, we have this time/slash axiom, yeah? And the time/slash axiom tells you that the algebra, the kinematic algebra, so the time zero algebra is essentially the same as the full algebra. So if you would have an ideal, it's already an ideal of the time zero algebra. It's not an ideal referring to the dynamics. Yeah, so I think it's so this is the in a sense, I think there's no formal proof that it's a simple algebra, but there is this formal proof that the time zero algebra, which is just the initial conditions, fixes already everything. So there is not so much freedom for quotients.
Okay. Yeah, so we can probably discuss it a bit longer, but yeah, let's finish the official part of the seminar. So let's thank Klaus again for the very nice talk and interesting discussion.